and the normal force of the plane with the tension force of this string. Your job now is to take the two measurements that I've given you and the equations that you have and calculate the mass of the truck. And then you'll come back and take another look at the video and find out, we'll measure the mass on a balance and compare to what you came up with. Now that you've calculated the mass, we'll find the mass on this scale and compare values. It's more than 500. I'll put that on 500 grams. And this one is on 40. And that's just about right. So we're going to call the mass of the truck 0.540 kilograms. Now you shouldn't expect to get exactly that value because there are some sources of error in this experiment. The strings may not have been exactly perpendicular and parallel to the plane. That's probably the biggest source of error. Another one is that the pulleys, even though that they move pretty freely, they do have some friction, and that friction actually helps out the weights hanging over the end, so they don't have to be as much in order to support the truck. Now, if you were off by more than about, say, 20 grams between the value on the mass and the value you calculated, then you may have made a mistake in your calculation. So go back and take another look at those. Now we're going to look at Newton's first law in a different way than we've been doing. Up until now, we've been looking at objects moving in a straight line, either speeding up or slowing down or staying at the same speed. But Newton's first law deals in general with objects whose velocity may or may not be changing. We know that velocity is a vector and has both a magnitude and direction. And so in this demonstration, we're going to look at changes in direction. Again, Newton's first law says that an object either remains at rest or in a state of constant velocity unless acted upon by a net external force. In this particular case, we're going to look at a force causing the object to change its velocity by changing its direction. We do this by swinging an object in a circle. We're going to use Bungee Man here for the object that we're going to swing in a circle. And as it swings in a circle, as you know, its velocity vector is always tangent to the path, and so that direction is always changing as Bungee Man swings. Now let's take a look at the force which is causing that direction to change. The force must be coming somehow from the elastic here. And in fact, you can see how big that force is, or you can estimate how big it is just by seeing how much this is stretched. So I'm going to start swinging Bungee Man like this, where it's not stretched very much. But as you see, as I swing faster and faster, that the cord will stretch more and more. Let's go down here slow to begin with. And then speed it up. And so you can see that more and more force is being applied, and that force is being applied first by my hand to the spring, and then by the spring to Bungee Man. And that force is a force which is pulling inward on Bungee Man toward the center of the circle. So in conclusion, what we've seen is that by applying a net external force, in this case to the center of the circular path, we're able to change the direction of an object's velocity vector. We're going to be looking at collisions where the objects stick together during the collision. Now I'll demonstrate the collisions and get some data, and later you'll use that data in order to determine whether momentum and kinetic energy are conserved in these collisions. We're using the same setup as in the past, a low friction track. The track has been leveled so that the gliders don't have a tendency to drift one way or the other. They move along it with fairly low friction, but they will slow down a little bit, so it's not completely frictionless. On each glider, there's a post-it note which is taped there, and the purpose of the post-it note is to trigger the photogate timer as it passes through, and that's how we measure the velocities of the carts. And you may have noticed it was a little bit difficult to pull these apart. The reason they stick is because there's Velcro on the front of them. I don't know if you can see it, but there's a piece of Velcro on each side and the opposite kind on each side of this one, and so they will stick. So for each collision, one cart is going to be stationary to begin with. I'm going to make it this cart right here, so it'll sit right there just in front of one photogate, and this cart just to the outside of the other photogate. The reason I chose the position like this is almost immediately after the collision occurs, this post-it note will pass through the photogate. So if there is any slowing down of the carts due to friction, it's not going to have time to slow down very much after that collision. So that minimizes the error due to friction. And for the same reason, this photogate is close to the other one, so that almost immediately after this post-it note passes completely through, it collides with the other cart. In fact, I can probably move that just a little bit closer. So that will minimize the error due to friction, and we should get better data. So I'll begin by zeroing both of the photogates and position this and give this a push. And let's see what the photogates read. This one is 0.158 seconds, and this one is 0.077 seconds. All right, well now what I'm going to do is put different amounts of mass in the carts and get some more data. So I'll take one of these bars. Now each bar is half of a kilogram, and each of the carts is half of a kilogram. So that makes this cart now 1 full kilogram with the load on it. This one is still a half. Get that one ready. Reset the photogates. Here goes. And the time readings are, on this one, 0.110 seconds, and on this one, 0.070 seconds. All right, let's change the bar to the other cart. So now this is 1 kilogram, this is half a kilogram. Reset the gates. Collision number 3. Now that one you can see slowed down quite a bit. So there might be a significant influence due to friction that you have to worry about. Okay, the time on this is 0.239 seconds. And on this one is 0.071 seconds. Now you may have noticed that this flag was going through the photogate too. So this flag went through first, and then it was followed by that one. And why doesn't this flag simply add to the time that was already there and give us an incorrect reading? The reason is that the timer actually, it will stop after the first photogate goes through, and it will not record the time for the second flag. It'll keep that in memory, so if we wanted to find out what it was, we could find out. But it doesn't actually display that. So that's how we can get away with that. Okay, I'm going to put another bar on this cart and move this bar over to here. So now this is 1.5 kilograms. This is half a kilogram. 3 times the mass. This cart is 3 times the mass of that one. All right, reset. And the times are 0.109 seconds, 0.078 seconds. Let's do one more collision. I'll take my last bar and put it on this one. So now we've got 1 kilogram here, 1.5 kilograms there. Reset. And the times are 0.159 seconds and 0.087 seconds. So with the data that you have, the times for each collision and the width of the flag, which by the way is 5.0 centimeters or 0.050 meters, and the masses of the carts, you'll be able to determine whether momentum and kinetic energy are conserved in these collisions. We're going to be investigating the motion of this toy fighter jet, which strangely enough is propeller driven. We're going to determine the speed of the jet in two different ways. In one method, we're going to look at the forces acting on the airplane and use Newton's laws and figure out the acceleration and the speed that way. In the second method, we'll measure the velocity directly simply by finding out how far the jet travels in a certain period of time and dividing the distance by the time. And then we'll compare the two methods. So one measurement that we're going to have in order to do this is the length of the string that the airplane is hanging from. So let's take that first before we put this airplane back into motion again. I'll just put a meter stick up beside the string. We'll start with it right from the pivot point, and it comes almost down to the airplane, but not quite. It takes another probably couple of centimeters, we'll estimate, to get to the middle of the airplane. So that's a total of 102 centimeters or 1.02 meters. Now let's take a look at the theory before we actually take the measurements. Let's look at the forces acting on the airplane from the side. Here we have the weight of the airplane. I'll just call that mg. It's mass times the acceleration due to gravity. And the string pulls on it with a tension force. Well, vertically, these are the only two forces acting on the airplane. We want to combine these and do a net force analysis in order to determine the velocity of the airplane. And to get the velocity, we need to know its acceleration. So first of all, we know that the airplane is moving in a horizontal circle, and that when objects move in circles, their acceleration is centripetal and is directed to the center of the circle. So the acceleration vector of the airplane is like that. Now it makes sense when doing a force analysis with circular motion to make the axes point, one of the axes point in the direction of the acceleration. So I'll make the x-axis point that way. And the y-axis just has to be perpendicular to that. It can point up or down. So the positive axes are in these directions. Now with those axes, let's look at the components of the tension force. I'm going to define the angle that the string makes with the vertical as the angle theta. And that also makes this angle equal to theta because these two lines are parallel and those are alternate interior angles. That makes this side equal to t sine theta because that's the side opposite the angle, and this side equal to t cosine theta. Now we're ready to write down that force equation. In the x direction, we have only one force, and that's this one right here, the horizontal component of the tension force. So that's t sine theta. And let's look at the vertical forces. The net force in a vertical direction. We have two forces. We have the vertical component of the tension, which is t cosine theta, and the full weight force, which is the other direction, so it's negative. And now let's do some physics and algebra to combine these two equations. First, we know that the object is not accelerating vertically. It always stays in the same vertical plane. So F net y is 0. And we know that F net x is the mass times the acceleration of the object by Newton's second law. So let's write down two equations. Ma equal t sine theta from F net x. And from the second equation for y, I'm going to bring the mg over to the left-hand side and have mg equal t cosine theta. Now, we want to solve these to get rid of the tension force because we don't have a way of directly measuring the tension force. Well, it's easy to solve them that way. We just divide one equation by the other. So we'll have ma over mg equal t sine theta over t cosine theta. The m's will cancel and the t's will cancel. And what we're left with is a over g equal sine theta over cosine theta. Now there's an identity that says the sine theta over cosine theta is equal to the tangent of theta. So the final result, taking the g to the right-hand side, is g tangent theta. So the acceleration of the airplane, which is directed toward the center of the circle, is g tangent theta. Now that's a centripetal acceleration, so that means it's also possible to express the acceleration as the square of the magnitude of its velocity divided by the radius of its circular path. And finally, to solve for v, taking the r to the right-hand side and taking the square root, the magnitude of the airplane's velocity, its speed, is the square root of acceleration due to gravity times the radius of the path times the tangent of the angle that the string makes with the vertical. So this is one method that we'll use to find the speed. We'll need to know what the radius of the path is and what the angle is. Now let's think about how we're going to find those things out. What I measured before was the length of the string. Well, that's the hypotenuse of this triangle right here. Okay. In order to get the angle and the radius